30. We have a gas at a pressure of 1.25 atmospheres. And we have a volume of 2.50 liters at a temperature of 0 degrees Celsius. Let's automatically convert that to Kelvin. Okay. Now the gas is expanded to 4 liters, so I have a new volume of 4 liters, and it's warmed to a temperature of 15 degrees C. Which is 288 Kelvin. And it says, what is the new pressure of the gas? Okay. So we look in our equations and we have one equation, the combined gas law, which has pressure, volume, and temperature changes. Pressure, volume, and temperature changes. Okay, and we want to solve for P2. So I rearrange my equation, get P2. Let's walk through those steps a little bit. If I want to get P2 by itself, I'm going to walk through the steps here. I'm going to multiply T2 to both sides. So I'll have P1 V1 T2 over T1 equals P2 V2. Okay. Now I want to divide both sides by V2. So what I get is P1 V1 T2 over T1 V2 equals P2. Okay? So I'm going to erase all that and rewrite it up a little higher so we can plug in our numbers and still have space on the slide. Oops, not T V2 equals P2. So now that I have my arrangement, I'm going to plug in my numbers. So 1.25 ATM times 2.50 liters times 288 K. Make sure to put that all in parentheses because we're dividing by more than one thing. And we don't want to get order of operations out of whack. Right? And when we correctly enter that in the calculator, we get an answer of 0.824 atmospheres. Right, moving on. Number 31. And gas at 25 degrees C. And just automatically convert all degrees Celsius to Kelvin. That makes it 298 degrees Kelvin. Okay, at a pressure of 0.75 atmospheres. And a volume of 0.5 liters. To what temperature does the gas need to be heated to have a pressure of 1.3 atmospheres? So what temperature, it says specifically what temperature, so a new temperature and a new pressure of 1.3 atmospheres. Okay, So it says in the question, it says at constant volume. So with that in mind, I can just take this out of my list. Okay, I don't really care about the volume anymore because it's constant. So the things that are changing are pressure and temperature. Okay, so we would utilize the combined gas law. Oh, not T2, T1. P2, V2 over T2, and since volume is constant, we just leave it out. Okay, and we're going to rearrange our equation to solve for T2. So T2 equals P2 T1 over P1. So plug things in, 1.30 atmospheres times 298 K over the original atmospheres, and we find that that equals 517 Kelvin. Okay, and let's see, does it want temperature in Celsius? Not sure, but let's find it out anyway. Minus 273 equals 244 Celsius. Now, as you're going through these problems and you're solving for new temperatures, if you get an answer that is like thousands of degrees Celsius, something probably went wrong. Okay, because if you think about it, the surface of the sun is around 3,000 to 5,000 degrees Celsius. So if you're getting many thousands of degrees Celsius, something probably went awry. Okay, so hopefully you would look at that and say, I don't think that's right. All right. Now our new thing is called the ideal gas law. This one is what we use when there are no changing things. Okay? The previous gas laws were all about what do we do if something changes. The ideal gas law just allows us to solve for individual pieces, not dealing with changes. Okay? Now we have this new thing, R, right? And that is called the gas constant. And R's units dictate all the rest of the units, okay? Pressure, volume, and temperature all must match the units of R. So previously we've been working in PSI and torr and millimeters of mercury. But now we have to be in liters, atmospheres, moles, and kelvins in order to use this equation. Now one thing that's not listed here is, what is this guy? So N is moles of gas. Okay? So pressure, volume, moles, and temperature. And because R is a constant, we always know that value. Okay? And for the purposes of the problems here, I'm going to be using a value of 0.08206. Okay, now if I round that, it's 821, right? But Sapling uses 0.8206, and that's the way all of my notes are as well. So that's what we're going to use moving forward. Okay. Now, looking at this problem, is there anything changing? Right, so let's make a list of what is here. There's a volume, which it's asking for, and it's moles, and there's a temperature, and there's a pressure. Okay. Are there anything changing is there anything changing? And the answer is no. So if there's no changes, I'm going to use the ideal gas law. Okay, so remembering that R, 0.08206 liters atmospheres over moles Kelvin. Okay, so we're solving for the volume, so we don't have to worry about that. Moles are already in moles. Temperature needs to be in Kelvin, so let's do that. That comes out to 292 Kelvin. And the pressure needs to be in atmospheres, so I need to convert torr to atmospheres. Okay, and the pressure comes out to be 1.0197. And I'm tracking at the third sig fig. Okay. So I'm going to take my ideal gas law and rearrange it to solve for the volume. Okay. So I'm going to divide P to the other side. So volume equals nRT over P. Right? So I'm running out of space on my slide, so I'm going to erase some of these things a little bit, just so that I can finish the problem. So volume equals 0.250 moles times 0.08206 liters atmospheres over moles Kelvin times 292 Kelvin, all over our pressure, 1.0197 atmospheres, 3 sig figs. Right, I have 3 sig figs in my moles, 3 sig figs in my temperature, and 3 sig figs in my atmospheres. So my final answer is going to be 3 sig figs equaling 5.88 liters. Right? So how do I know it's liters? Well, let's go through the units. So here we have moles divided by moles. So moles will cancel out. I have kelvins on the bottom times kelvins. So kelvins will cancel out. And then I have atmospheres on top divided by atmospheres. My atmospheres cancel out, leaving the only unit left is liters. We have a mixture of oxygen, nitrogen, and carbon dioxide gas in a sealed flask. And the mixture has a volume of 2 liters, a pressure of 1.25 atmospheres, and 23 degrees C. What are the total number of moles? So we could look at what's changing, which is nothing, right? We're just asking a question. And the only equation that we have that has moles is ideal gas. Okay, so we have pressure, 1.25 atm. We have volume, 2.00 liters. Moles, we don't know. Temperature is 23 degrees C. Makes it 296 K. And we know R always, because R is a constant. Right, so if I rearrange my ideal gas law, I find that PV over RT equals N. So 1.25 atmospheres times 2 liters divided by, not a circle, divided by 0.08206 liters atmospheres over moles Kelvin times 296 K will equal 0.103 moles.